Hi everyone and welcome to this video. In this video I want to talk about the linear combination of vectors. So let's understand what they are and then I'll do some examples for you. So given that we have alpha sub I, these are real numbers, and we have v sub I, these are in V, which is a vector space, and then we have U, a vector, which is also in V. And again, instead of alpha sub I, you can put C sub I. It doesn't make any difference, just different notations. These are just constants. They're scalars, and these are vectors, and U is a vector. If we write U as alpha sub 1 times V1 plus alpha sub 2 times V1 plus dot 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 alpha sub n times Vn, or we can write that in summation notation, sum of alpha I times Vi, I starting from 1 to n, then we say U U is said to be written as a linear combination of V1, V2, and Vn. Let's do some examples so you can understand how this works. For example, in R2, we're given two vectors, V1 and V2. If I say to U equals to 2 times V1 plus 5 times V2, that means 2 times V1 is that, plus 5 times V2 is that. So you get 2, 4, plus 20, 15, and you get 22, which is the X component, and 19, which is the Y component. So here we say U is written as a linear combination of V1 and the V2. U is 2 times V1 plus 5 times V2. With matrices, again, if I have a matrix A, 1, 2, 3, 4, I can write that as 1 times this matrix, which is 1, 0, 0, 0, 2 times that matrix, 3 times that, and 4 times that. So if we multiply all these numbers to those matrices and add those matrices, then we get the matrix A. So that's pretty straightforward. So we can say A is 1 times B1 plus 2 times B2 plus 3 times B3 and plus 4 times B4. So A is written as a linear combination of B1, B2, B3, and B4. Another example with polynomials, if I have this polynomial, or this is a quadratic function, P of x is 3x squared plus 2x plus 1. P of x can be written as 3 times x squared plus 2 times x plus 1 times 1. So we said P of x is written as a linear combination of x squared, x, and 1. So these work for all the vector spaces we learned in the last video. Now finding linear combinations, let's do an example of that. In R2 we have two vectors, V1 and V2. So V1 is 1, 2, and V2 is 2, 3. Now the question is, can W, which is the vector with components 5, 8, be written as a linear combination of V2 and V1 and V2? Now how do we do that? If you want to find that out, you can just say we don't know what those numbers are. You can call them X, Y, C1, C2, alpha 1, alpha 2. It doesn't make a difference. For this first example, I call them X and Y so you see what's going on. So X times V1 plus Y times V2 equals to W, and there's a question mark here. So X times substitute, X times 1, 2, and Y times 2, 3 equals to 5, 8. So if you multiply X, 2X here plus 2Y, 3Y here equals to 5, 8 again. Add those X plus 2Y, that's the first component. And the second component is 2X plus 3Y, and that equals to 5, 8. Put the components, excuse me, components equal to each other. So X plus 2Y equals to 5. and 2x plus 3y equals to 8. And we see this is a system. So that's why we have been solving all those systems, and we're going to change them to vectors. So if you want to write the system, that means again, you write the matrix. This is the coefficient matrix. This is the matrix of the variables, and that's the constant matrix. So the equation is basically 8 times x equals to b. And I did the row reduction for you. So if you put the coefficient matrix again, 1, 2, 2, 3, and here 5, 8. If you do negative 2r1 plus r2 and you change r2, so you want to make that 0, so that becomes 0, that becomes negative 1, and that becomes negative 2. Then you want to make that 1, so you multiply r2 by negative 1. So you get 1, 2, 0, 1, and that becomes positive 2 also. Then you want to make that 0, so you do negative 2r2 plus r1, and you change r1. Basically what you do, you get the identity matrix here. Now what we got is x equals to 1 and y equals to 2. What's the meaning of that? 1 times v1. So v1 plus 2 times v2 equals to w. You can double check the answer here. So 1 times 1, 2 plus 2 times 2, 3 is going to give you 5, 8. Let's see what happens graphically. So this is the vector v1. They're pretty close. That's the vector v2. 1 times v1 is just v1. It's right here. That's what I'm doing. And 2 times v2 is double that vector. So I wrote it here. And if we add that vector to that vector, we get 5, 8, which is w. And that's that vector. So that's graphically in R2 is pretty easy to check. Now let's do another one, another example, finding linear combinations. This one is in R3. So this one I wrote the set. So in our set we have V1, V2, and V3. And these are the components. So the question is, can U, which is the vector with components 5, 2, 1, be written as a linear combination of V1, V2, and V3? Now, again, here instead of using X, Y, Z, you can put alpha, or you can put C's. I use C's here. C1, V1 plus C2, V2 plus C3, V3, is that equal to U? And this becomes a system. If you want to, and we know it's a system, if you want to find that system, write that system fast. So you can just, here I put C1, C2, C3. So for C1, as you see, you have those components. So 1, 3, 1. For C2, you have those 3, 0, 1. And for C3, you have those. So these are the columns. And I also put X, Y, Z. Just again, I use C1, C2, C3, but this is the same thing as X, Y, Z. Now you write the augmented matrix, and if you do the row reduction, you do get the identity matrix. So here C1 is 0, C2 is 2, and C3 is negative 1. What's the meaning of that? Let's check. 0 times V1 plus 2 times V2 plus 1 times V3 should give us U. 0 times, that was V1, 2 times V2, and negative 1 times V3. And if you do that, you get 5, 2, 1. Let's check one of them. 0 times 1 is 0, plus 2 times 3 is 6, minus negative 1 times 1 is 1. 6 minus 1 is going to give you 2, and it will work for the other two. Now I put a note for you here. The system, when you write that system AX equals to, we must have at least one solution. If the system does not have a solution, then the answer will be no. You can't write it, for example, here U as a linear combination of v1, v2, and v3. Let's try another example. Same way, we are in R3, we have 3 vectors, and these are the components. And in this case, U is 1, 1, 1. So can U be written as a linear combination of V1, V2, and V3? Again, if you want to write the system or the augmented matrix fast, this is for C1. So it's 1, 2, 3, 1, 2, 3. And for C2, so it's going to be 0, 1, 2, which is right here. And for C3, we have negative 1, 0, 1, negative 1, 0, 1. And of course, this is the vector, the components of the vector U. Here again, if you do the row reduction, we notice it's a little bit different. So we do got all zeros in the last row. So that means this has infinite number of solutions. So here our free variable is C3. So if you rewrite the system, you get C1 minus C3 equals to 1 C2 plus 2 C3 equals to negative 1. So the free variable is C3. You can say C3 is T, then C2 is going to be T plus 1, and C1 is going to be T plus 1 right here, and C2 is going to be negative 2 minus 1. Now let's try some numbers. I tried 2 of those. If T equals to 0, then C1 is 1, C2 is negative 1, and C3 is 0. Let's check. 1 times V1 minus 1 times V2 plus 0 times V2, is that equal to U? All you have to do is substitute. So 1 is right here, negative 1 times V2 is right here, and 0 times V3. Let's try one of them. 1 minus negative 1 times 0 is 0, and 0 times negative 1 is 0, so we're just left with 1. And here we have 2 minus 1, and this is just 0, is going to give you 1. And finally 3 minus negative 1 times 2 is 2, is going to give you 1. So what we get is 1, 1, 1, and 1, 1, 1. Now if you pick C, T equals to 1, then you get those numbers for C1, C2, and C3. And if you try the same, you're going to get again the right answer. Check 2 times V1 minus 3 times V2 plus 1 times V3. Is that equal to 1, 1, 1? And the answer is yes. Please check that yourself, and you'll see you get the same answer. So that's how we write the linear combinations of vectors. And in the next video, what I'm going to do, I'm going to talk about spanning vectors. So spanning or vector sets. I think that's it about this video. Thank you for watching. Again, watch it 2-3 times and try some more examples yourself. And I'll see you in my next video. Have a good one, everyone.